Mhm.
So yeah, welcome to the second Leetcode mock interview today on your favorite Sunday
Mhm.
installment on Twitch. I'm joined today by Minh, who is our volunteer from the crowd. Do you want to give a quick introduction about yourself?
Yeah, definitely. Hey guys, I'm Minh. I I was here 2 weeks ago, and I didn't expect to be here again this soon. So I did mark this interview as like a hard difficulty, but I was expecting it to be like a month and a half later, but we see how it goes. I'm really excited.
Yeah, for sure. Yeah, the reason it was because I was grabbing the schedule people in this week because I'm actually on vacation starting next week, so I won't be
I
here for
see, I
like a
see.
month and a bit. So I was just asking a
Hmm.
whole bunch of people who could come in because this weekend we're actually doing six of these sessions instead of just a regular
Oh
four.
Lord.
So that's why
Oh Lord.
I was just trying to get people on. So that's why you're up a bit early, but that's not a problem at all. So let's get started to the problem then. So as always, you're welcome to take notes. Slow me down if you have any questions. And
Hmm.
otherwise, I mean, you know the drill. This is a leak code, so let's get into it. Okay, so are you ready to take notes if you need? Let me just make sure my notes are good too. Great. So today's problem is going to be a GCD traversal. Okay.
Hmm.
So the input is going to be. So I want you to write me a function that can perform this task. And I'll explain this task in a bit more detail later. It's a bit more involved. Okay. So
Okay.
the input of this function is going to be a list of numbers, and the return will be true. It will be a boolean. Okay. And so here's how it's going to work. You're going to return true if and only if you're able to traverse between any two given indices of the array. Okay, and what it means to traverse between the indices is if the two indices share a GCD that is greater than one. Okay,
Mm.
and so your goal is to return true if and only if it's possible to traverse between all such pairs. Okay,
Hmm.
let me know.
I see.
Yeah, this can be a bit more involved. So let me know, your kind of initial thoughts on this one.
Hmm. Uh, I guess like my initial thought is like for traverse, what do you mean by that? Like, are we outputting the path of the traversal, or
You're only
are we trying to?
outputting a boolean.
Oh,
True.
if it's traversable,
Yes, if you're able to traverse between all pairs of indices, essentially.
all pairs of indices. Right. All pairs. That means that if I could traverse, let's see, traverse between all pairs. So does that mean that I would be able to visit every number? Is that what it essentially means? I don't
Almost.
know.
So let's say we have an array.
Hmm.
Let's say this array has values 2, 3, 6.
Right. Okay.
Okay. So
Hmm.
this array is traversable if and
Hmm.
only if it is possible to traverse between all pairs of indices in this array. So, what are the pairs of indices in this array? We can go through this example.
Hmm. I see. So,
So one pair is 2, 3,
right. And the
and
other pair
then
would be 3, 6,
there's one more.
and that'd be 2, 6. Right.
Uh huh.
Okay. And you're saying that if we could traverse, like if you could go through all of this pair?
Yeah. So a pair is traversable
Hmm.
if they share a GCD that is greater than one.
If they share a GCD that is greater than one.
So let's so
Oh,
let's
so.
so let's talk about that.
Hmm. Hmm. Okay.
So let's talk about that, right? So these are the three
Hmm.
pairs.
Right.
I'm gonna just do this because we need a bit more space. Okay.
Yeah, yeah.
Okay. Is does 2 and 3 share GCD greater than one?
Hmm.
Does it? Is the question?
Um, like, are we, sorry. So when you say like these two pairs, like these four numbers, are these three different numbers?
Nope, not quite. So we're only considering pairs of two right now.
Oh, pairs of two.
So there are
Oh,
three
so,
pairs of two in this array,
right.
correct? Two, three.
Three
There's two
pairs of
right. There's three combinations of unique indices.
right. Yes, yes.
Correct. So one pair of
Mm-hmm,
this is combinations index 0 and index 1, which is values 2 and 3.
mm-hmm.
Correct.
I see. Mm-hmm.
Does 2 and 3 share a GCD greater than 1? No.
No.
No. Okay.
It's just one. Yeah.
GCD. No. Okay. How about 3 6?
Yeah. It should be three.
Yes. How about 2 6?
Yeah.
Yes. Great.
Two.
Now,
Mm-hmm.
there's one more note, which is you can still traverse between 2 and 3 because you can go from 2 to 6 and then 6 to 3.
I see.
And so all paths used to traverse between 2 and 3 have GCDs greater than 1. And therefore, but has path.
Oh, I see.
Therefore, transitively, it is possible to traverse between 2 and 3 using only paths that have GCDs greater than 1. Does that make sense?
Mm-hmm. Yeah. Yeah. It's a lot clearer now.
Great, yeah.
I see. I see.
Yep, so
Um,
your task is to, given a array of numbers, return true if and only if it is possible to traverse between all pairs.
between all pairs. I
Mm-hmm.
see. I see. Can I see. Is it possible if I try and rephrase this
Of
question
course.
to make sure that I understand?
Yeah.
So, because yeah, okay. So right now, because I was a little bit confused about what it means to be able to traverse between all pairs. But if I imagine it as like a node within a graph, so two, we would have like two as a node and three as a node and six as a node. So if I'm able to traverse all pairs, that would just mean that between any two nodes, like I would be able to reach it, right? Like there's a path to reach two nodes, right?
Yes. If there's a path
That's
to reach true nodes, it doesn't have to be direct,
ah, I see,
right? It does
I
unless
see, I
there's
see,
a path. Yes, then they're considered
I
traversable.
see. I see, I see. So this would be ah, I see, I see, I see. So, hmm, okay, that's good. Uh, it's definitely a difficult problem to wrap my head around. Yeah. So I guess like the pair would just be like the source and destination essentially.
Yeah,
Okay.
that's how I want to look at it. Yeah.
Mm-hmm. So GCD that has all path greater than one. Let's see. And we're returning true if all path greater than one. Mm-hmm. Implicity just means greatest common divisor as well.
That's right. Yeah.
Yes, yes. Mm-hmm. So right now, my first intuition is, or like my first problem that I should try and approach is that how I could convert um how I could convert like this input to like a graph that has like all the different edges and all the different nodes. And from there it's just a simple graph traversal problem.
Okay.
Um yeah, so that's my first intuition right now. I can't really think of a better way to go about this, but I think I'm just gonna work on this for now, and then if I find something better, then I might propose it later. Does that sound good?
Yeah, that's fine. Yeah, that's totally good.
Okay, sounds great. Okay, so let's get started for this then. So right now, I could divide this into two sub-problems. One of them is to um yeah, one of them is to generate. So there are two sub-problems that I need to solve right now. So one of them would be generating like all the different pairs within the array. Um, all pairs within the array, so that I would know. Yeah, so I would just generate all different pairs within the array, so I could potentially go through them all and filter out the pairs that that are not eligible for um, for the graph, and I'll explain what eligible means in a quick second.
Hmm.
But the second problem that I'm also facing right now is to find the GCD of like the pairs. Um, and to find the GCD of the uh of all the pairs after I generated them. And yep, find GCD of pairs. And when I say like filter out which pairs are eligible or which pairs are valid, that would just simply mean that just go through, just generate the GCD for all the pairs and then filter out the one that doesn't have GCD greater than one. Because if it's not greater than one, then there's essentially no edge between the two nodes in that pair. Does that make sense?
Can you repeat the last part? If there's no
Yeah.
GC greater than one.
Yeah, so if because right now the way I'm looking at this is like a pair is representing a possible edge between the two nodes. So if two and three are together, like it's we're thinking like there may be an edge between two and three. But if their GCD is not greater than one, then it's not a valid edge. So like
Mm-hmm.
we just gonna filter it out. So that's what I
Mm-hmm.
mean.
Yep. Okay.
Yeah. Okay. That looks good. But yeah. Yeah. Um. But yeah. But I think that's gonna be my approach for now. So I'm gonna generate all the pairs, and then I'm gonna find the GCD of each pair, and then I'm gonna remove all the pairs that don't have GCD greater than one, and then it's just gonna become a simple graph traversal problem. And that's basically, I think that's gonna be basically my approach, my initial approach. Does that make sense? Can I?
Yeah, we can go with that. Yeah.
Nice, nice. Okay, okay. Hmm. Okay. So let's think about this. I'll just quickly make the function signature for for our solution. So it's gonna be uh is traversable by GCD. GCD. Okay, and then it's gonna take an array of vector. I mean, a vector of
Yeah.
numbers for the graph. I mean, as an input. Um, speak of which, I guess are there any constraints on like the numbers? Like, can there be negative numbers? Can there be negative numbers and can there be like decimal numbers
We can assume
within?
that all the numbers are positive integers.
Nice, positive. Okay, that sounds good then, because yeah. Um, okay, positive integer. And I guess like a separate question I would like to ask as well, is there like an upper limit to the number? Because I know that in C++, an int is only 4 bytes. So working with anything that's larger than 4 bytes is a little bit concerning.
Oh, it's actually only 4 bytes. Oh, it can be.
Uh,
It's up to the. Okay, let's. 4 bytes is fine for now. We can see if that's causing an issue. So yeah, whatever the
okay,
4 byte limit is, positive. Yeah.
yeah, okay, sounds good then. Vector. Okay, uh, sounds good. Reversible. Okay, I think I'm just gonna tackle the first subproblem first. I'm just gonna start with the generate generate all pairs within array. Um, so like the problem with generate all pairs, it's pretty simple to do. Um, all you need is just like a nested loop, and I would take I would pair I to every number after I, for example, and then so on for I plus one and I plus two.
Mm-hmm.
So it's not a very difficult problem to do. So I could be I could have something like um like edges, for example. So I'm gonna have a list of edges. Um, okay, and then I'm gonna go through all the numbers in the array. Oh shoot, probably cannot do this. Um, okay, okay. So I'm gonna do my first loop first. Same thing for here. Yeah, and as I mentioned, this will start at I and for every number after I. So let's say index K, for example.
Mm-hmm.
Um, but yeah, this would definitely generate all the pairs for me. So all I have to do is adding the pairs um to my list of edges. And that would be, say, for example, I and J, for example. Um, yeah. So this would generate all the pairs, but there's also condition of like all the pairs need to have a GCD greater than one. And instead of like going like having a second pass and trying to filter them all out, I could
Mm-hmm.
I could do like a check here first, and then I only include the ones that are valid.
Yeah.
Uh, yeah. Okay, sounds great. So I think I'm gonna create a helper function here. Um, say I could call it find GCD, honestly. Find GCD, and so to find a GCD, like a greatest common divisor of I would need two different numbers. So if like say number one and number two, for example. And yeah, and I would need an algorithm to essentially find the greatest common divisor for both of them. And oh, oh. Okay. Okay. So I guess like this is gonna be the meat of the problem. So how can we find the GCD of two numbers? Um, right now, like on the top of my head, because I remember working with I cannot remember the name, but is it the Euler's method? That was
Yeah. Euler is one method. Yeah.
yeah. It's the Euler's method um that one could use to find a GCD. And what it essentially does is that there are actually two different variations to it. Let me see if I could remember. Um, okay. So what it does is that it takes um the larger number. Um, sorry. Okay. It what it does is that it takes a larger number and it's do a modulo operation on the smaller number. Um, uh,
Mm-hmm.
I'm getting a little bit nervous here because okay. Um, okay.
Let's. Okay. This is this the only GCD method you know?
Um, because I also uh I could also what I could do is I could also iterate between one to 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 the no to the lower number and find which number in that range is divisible by two numbers, and I would take the largest one. So that is like the more brute force way.
Do you need the largest one?
Sorry.
Yeah. Okay. That way works too. Um,
Yeah.
Tell you what. Let's assume that find GCD is implemented for now, and come back to this if we have time.
Sorry.
So let's assume that find GCD is
Uh,
given, and we'll come back to it
I
if we
see.
have time.
Okay. Sounds good. Sounds good. Okay. Yeah. Okay. That makes my life much easier. But yeah. So if we assume that find GC, like we already implemented find GCD with like a nice Euler's method.
Mm-hmm.
What I could just do is that I'll just grab the GCD of two numbers between number at index I and the number at index j, and I'll check if it's greater than one or not, and
Mm-hmm.
then I would know that this edge between these two numbers are valid, and I would just push it to the list of edges that I could use to essentially construct the graph later. Makes sense, right?
Mm-hmm. Okay, yeah.
Sounds great. Sounds great. Um, that sounds good. Okay. And now what can I do? Um, okay. Now that we know that we have a list of edges, I could potentially, what I could do right now is, what I could do is construct a, uh, an agency list where, for each node, I would know the adjacent node, and I could just, uh, I can essentially go to that node and explore the entire path.
Okay.
Uh,
Sure.
so yeah, yeah. So what that means is that I would just go through the list of edges, and I would just take uh for each edge, I would need like a map that maps the node to its list of adjacent nodes. Um, yeah. So I would map a node to the list of adjacent node. But now that I think about it, I don't really need, yeah, I don't really need to store a list of edges first and then construct it. I could also just make an order map, and then construct it as I go as well. So I would map it with a list of adjacent nodes. Let's say call this graph, for example, and let's add an order map. Okay. So what can I do here? I could potentially add, oh, yeah, yeah. So what I could do is that, so this, for this graph, it would be a non-directional graph,
Mm-hmm.
uh, which means that like it could, between two nodes, it could go either way. So what I need to do is um, I would need to push each node to the other nodes list. So here I would need to push the node at K to the list, to as like an adjacent node for the node at I, and same thing for node at I to the list of node at J as well. So it would be something like this. And yeah, and for C++, the convenient thing is that it would just, if a node didn't exist in the graph yet, it would essentially just create an empty array for me to push it back. So this is a pretty neat way to construct the list. Yeah, to construct the adjacency list.
Mm-hmm. Okay.
Um, yeah, and now what I can do, uh, is that I could traverse the I could traverse the graph and make sure. Yeah, I could traverse the graph and grab all the. I could traverse the. Oh, right. I see. So how can I make sure that every node is connectable, is traversable? Um, I'd say if it's. Hmm. Let's see. I'd say if a graph is connected, if a graph is connected, um, any node, any node within the connected component, is traversable. And let me know if I'm going a little bit
Nope,
if
keep
I'm
going.
doing this a bit directly. Yeah.
No, that
Okay.
makes sense.
So yeah. So every node within a connected graph will be traversable, and there's a chance since we creating the graph from scratch, there's a chance that two nodes, I mean two there could be like unconnected components, like two components are not connected to each other. Like there's no edges between two components. So how do I detect this? Mm,
So I like that you are talking about graph connectedness, right?
mhm,
And just to be clear here, we're basically saying return true if and only if the graph is connected.
mhm.
That's what we're trying to solve, right? Just to be
Yeah,
clear. Great. Okay.
yeah, 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 essentially. Yeah. Uh, yeah, yes. But how do I find? Oh, it's actually, I don't think it would be a too difficult of a problem to solve. Because what I could just do is that I pick a random node and then, yeah, I would just pick a random node, like say the first node in the array, and then I traverse the like all the possible path, all the possible edges that I go. And if the and I then I keep track of the number of nodes that I've been through. If the final number doesn't match up with like the original number, that means that there's like a unconnected component here, and it only consists of like say um n minus j nodes for essentially. Does that make sense? When phrase it like
Uh,
that?
I think so, but I wanted to just maybe back up if possible. So, what
Hmm.
what is like? So yeah, we're trying to determine the graph is connected. What
Hmm.
general strategies are there to determine if a graph is connected?
Oh, yeah. Um, so I mentioned that we could traverse the graph,
Traversal, yes.
and yeah, we could traverse the graph to see if it's connected or not. Traverse and then count the number of nodes. And by traversal, we could either do depth of search or breadth of search. Either way is fine with me. Either way is works. And yeah, and that would be I think that would be a pretty nice strategy
Okay,
to do it. Like yeah, traverse through the graph and count the number of nodes essentially.
sure, yeah, that sounds fine with me. Let's proceed with that.
Sounds great. Sounds great. Sounds great. Um, yeah. Okay. So if that's the case, I think I'm gonna go with oh, shoot. I think I'm gonna go with breadth search, and it's not because I don't. It's because for depth search, I could also do it like I guess I could also do depth search iteratively, but it's much easier to do uh breadth search iteratively. But for depth search, if I were to do it like recursively, if there are a lot if there are a lot of nodes in the graph, we might use a lot of memory to build the stack frames for the functions. So I guess in this case, it's best to just do breadth search to traverse the entire graph. If there's no advantage to either one of them.
Sure, let's do
Yeah,
BFS.
sounds great. Okay. Uh okay, okay, so for BFS, the most important thing is the queue to yeah, to do a breadth search through a graph. I would need a queue to um I would need a queue to um to keep track of all the nodes that I need to go through, kind of in order, if that makes sense. So what I need to do first is to initialize a queue for the first in first out order, and I would call this like say to-dos for example. And you, oh no, okay. I thought it, yeah, okay. And then As I mentioned, I would just pick a random number, a random node to start with, and I would just start with um, um, the first, the first node that I found in the input list. And so let's see, this would be function set. Okay, and then there's a like since this is a graph, there's a chance that um, since this is a graph, there's a chance that there are cycles, and I also don't want to go to A. I mean, from A go to B, and then from B go back to A,
Mm-hmm.
because I saw the edge in both sides, right?
Yep.
So what I also need is a is an order set to keep track of all the nodes that I've been through. If if like one of the child node of the next node has already been visited, I wouldn't try and visit it again, because yeah, because that would lead us to a infinite loop. So yeah, I'm just gonna do that then. I'm just gonna add an order another set here. Don't mind me. And it would be also in on the set of numbers. I'll call this visited, since it's pretty descriptive what it's gonna do. Okay. Now what we can do here is that while we still have like nodes to visit, we should try and visit all of them. So what you could do is like if the to-do list is not empty, let's try and visit all of the nodes in there. So what can I do here? What I'm gonna do is that I'm gonna grab the list in front of the queue, and start processing it. So I would call this a node, for example, call front. And then uh, I'm also gonna pop the node and remove it, like essentially remove it from the queue. Um, if I remember, that would pop. Oh, nice. Yeah. So we grab the node at the front of the queue and then remove it from the queue. And
Mm-hmm.
then I should probably add it to the visited list. Oh, oh, node. Nice. What I can do here is that since I have like a license list, I could just go through all the children and add it to the to-dos list so that I could come back and visit and process them later. So what I can do here is go through all the node um, in the adjacency list, and that would be graph. And first, I would need to check if the child is already in the visited list, because if it is, I shouldn't bother checking it, like I mentioned. So visited, find child. So check if it's in the list already. Oh, okay. So if the child is already in there, then just skip it. If it's not, then I'll just push it to the queue instead. Oh,
Mm-hmm.
yeah. And yeah, I also mentioned that I should keep track of the number of nodes, and then compare it later to see if it matches with the original number or not.
What's the visitor set
Uh,
mean?
Visit set is just it contains all the nodes that has already been visited. So
Yeah.
uh,
And you're currently
so
trying to
yeah.
find a variable to find the number of nodes you visited.
Oh, yeah, you're right. Yeah, I guess you're right. I guess it's all since it keeps track of all the nodes that have been visited. It also has like all the nodes, all the number of like the number of nodes that has been visited as well. I see. So yeah, you're right. I don't need to keep track of an extra variable for that. And at the end, I could just do like a simple comparison to check if uh the set has the same size as the original array to determine if the graph is connected or not.
Mm-hmm.
And this would be my final implementation.
Great.
So yeah,
Let's talk about the time and space complexity.
time and space complexity. Yeah.
Mm-hmm.
Hmm. Um, yeah. So for okay, let's go through this one by one then.
Mm-hmm.
To generate all the pairs within an array, um, since since I would go from I mean, yeah, since I would go um from I to I plus one to n, and then wait, sorry, let me rephrase that. So since I would go from I to n, and then go from I plus one to n, and from I plus two to n, there's a time complexity of O of n for that
Mm-hmm.
because I'm essentially visiting each node um like multiple times, like at least n times,
Yep.
right? And yeah, and within those, and as I generate the nodes, the GCD function, I cannot remember what's the original time complexity for the optimal GCD solution is.
We can just call this G
Um,
for now.
okay, G. Sounds great. So I guess um, so if find GCD takes G time,
Mm-hmm.
and we do it like and we do it n time here, and and we go through the list n times again. I guess the time complexities for this would be O of n squared times G, where where n is the number of where n is the number of numbers within array.
Yeah. Okay.
Yeah, makes sense. Sounds good. Sounds good. And say uh okay, and say for in the worst case, every node has a GCD greater than one. That means that every node is traversable to each other. We would have like uh n square of edges.
And
Wait,
in
sorry.
squared edges. Okay.
Not n square of edges, but um um yeah, if we um sorry, let me gather my thoughts real quick.
Mm-hmm.
I'm not too sure what about the number of edges here, but what I do know is that since we try to go through every node only once, with the visited set here,
Right.
we only go through like we only go through n nodes. So this entire traversal graph would only take all of n times, where n is the number of nodes, and 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 yeah, and that would
Okay.
only take all of n times. Does that make sense? Am I on the right track here?
Yeah, that makes sense. Yeah.
Sounds great. And for the space complexity, it's a little bit harder.
So what's the overall time
Be
complexity?
oh yeah, the overtime complexity would just be so since it's O of n squared times g plus O of n, it would just be I can just like simplify it to O of n squared times g, and yeah,
Okay.
and depending on how fast g is. Yeah, so yeah, the total complexity would be O of n squared times g.
Okay. For time.
Um,
Yeah.
nice. But for space complexity, yeah, so for this one I need to do a better analysis. If every node is traversable to each other, that means that for every node we have n edges. And since we have n nodes, so we have n entries here, and for each entry we have n nodes. So that would uh we would probably look allocate O of n square of extra space, and assuming that GCD takes constant space. Does that make sense?
Yep.
Sounds great. Sounds great. So O of n square extra space, and for the Q, si like I mentioned, since we only storing the valid nodes to visit, it would only take up at most O of n. I mean, at most n nodes. And same thing for another set, for the set as well. It would only take at most n extra space for the n number of nodes. And yeah, it would take at least, and since we're doing iteratively, we don't have to care about the extra stack frame that we need to allocate for. So like the final space complexity would just be O of n square. Yeah.
Okay. Yeah, those sound right to me for this implementation. Let's talk. We have about 5-10 minutes here. I want to spend a bit of time talking about optimizations for this problem. Okay.
Mhm.
Um, Obviously, the bulk of the complexity for both space and time is the fact that you're generating a adjacency list,
Mhm.
right? Um, and the reason you're generating this adjacency list is because you want to map numbers to other numbers.
Mhm.
Right? In other words, your nodes are numbers and your edges exist if they have a valid GCD, right? So this is a
Mhm.
pretty literal interpretation of the problem statement, and it's correct, right? Now,
Mhm.
one thing we can keep in mind, one thing we can remind ourselves is that there are some other properties that we can look at, and so for example, we can consider modifying. Uh, we can modify some of this algorithm to take advantage of the fact that prime factors can simplify a lot of the need for adjacency lists.
Mhm.
Are you familiar with prime factorization?
Uh, I'm not too sure about it.
Like not just in code, but in general.
Oh, like what prime factors are? Or...
Yeah, what it means to produce a prime factorization of a number.
Yeah. It's to find all the prime factors of a number, right?
That's right. Yeah. So in other words, all numbers can be represented as the product of some number of primes. Every
Right.
number, right? Every integer,
Mhm.
positive one, right? And so the prime factorization determines the prime factors of a number, right?
Right.
So we can assume that's implemented. We don't need to implement that. Um,
Mhm.
can that help you with this need for GCDs?
Would that help me with this need for GCD?
In other words, if two numbers
Hmm.
share the same prime factors,
Hmm.
they must have an edge.
Yeah. Yeah, that makes sense.
Mm-hmm.
Okay. Uh, yeah, that makes sense. Um, I'm just trying to digest it right now.
Yeah,
So if there must be an edge, and would that be like an optimization to GCD, or would it be an optimization overall
that would be an optimization overall to the
to the
backing
function?
structure of your search. Um, I would say, yeah. The problem is a bit more difficult to think about this way because the literal interpretation of the problem you have solved. I think this is a valid solution.
Hmm.
But as you know, it's actually highly inefficient. It's an n squared algorithm, right?
Hmm.
And so we can actually speed it up a pretty good amount if we instead did the opposite mapping. So
Opposite
the
mapping.
opposite mapping, right? The opposite mapping, as in, we store like we map a prime number to the numbers that have that prime number as a prime factor. Do you want to write that down really quick?
Uh, yeah. So, so does that mean that? Oh, I see. So if like say my number is six, for example, I would map two to six and then three to six. Is that?
That's right.
I see. And how does this help us? Hmm.
So um, there's so let's say, so in this case, I was a bit ambiguous. So let's be a bit more clear now. So in this, oh whoops.
Hmm.
So let's say in this case, right, we define this as O of G. The reason it's O of G is because G is the size of the number, right? So we say
Hmm.
G equals size of number. Let's say in bits, for example. It doesn't really matter, right?
Right.
There can be, so that what that means is that there are log n prime factors proportionally, right? If there's n numbers,
Hmm.
uh, there can only be at most log n prime factors. Is that clear?
For log n.
Yeah. So yeah, right. So if you have if you have g number, right? So you have some number, some size of numbers. Sorry, size of numbers.
Hmm.
If your
Right,
number
right, right.
has g bits,
Hmm.
how many, like, what's the maximum number of prime factors you can have? It's up to root of that number, right?
Ah, I see, I see.
Right. So you can only have
I
at
see.
most log bits number of prime factors.
Hmm. Okay. Ah, I see.
Yeah. What and so now what can you do with that? So if you took
I
your
see.
original example of what was it, 236, right? So
Hmm.
okay, 236 is a bit trivial, but yeah. So this is your um. So two. So this would be 2 6. This would be 3 6, right?
Hmm.
Okay. So this is your state. So you generate this state. Okay. What's your next step going to be here?
Let's see. 2 is mapped to 2 and 6, and 3 is mapped to 3 and 6. Do I find, do I try and find like the common numbers between these two lists?
Mm-hmm.
Oh, I do?
That's right. Well, yeah, because the only way you can navigate between 2, 3, and 6 is
Hmm.
if a 6 shows up in both. In other words,
Right,
2 goes to 6, 3 goes to 6, and then 6 is the same number. So 6 goes to 6.
right. Okay,
Right.
that makes
This
sense.
drastically reduces the space from n squared to
Oh, I
log
see.
number of bits,
It's a lot number of bits.
which is
Okay.
constant technically, but not actually.
Yeah, yeah, makes sense. Okay, I see. But then the problem arises of like how can we detect that all the numbers in the input array like share some common list, right?
Mm-hmm.
I see, I see,
Can
I
you do
see, I
that? Can
see.
you do that better than n squared?
Can I do that better n square?
That's the question essentially. Right.
Hmm.
This is a possibility. Let's spend a bit of time and analyze this a bit. We'll spend maybe like
Yeah.
2 minutes thinking about this. Otherwise, I'll just be. It's not too much. It's not too
Hmm.
much use. Yeah. Have a
I see,
think.
I see.
Yeah. Have a think.
Hmm. Can I also like think out loud here?
Yeah. Of course. Please.
Okay, so I'm just gonna so if I have two lists and I'm trying to essentially to see if two of those lists kind can I share some kind of intersection? Is that's what kind of what I'm
Uh huh.
getting out of here.
Okay.
So say I have 2 6 and then I have 6 and 3. So these two can be merged together. Like these two have an intersection of 6 right here.
Mm-hmm.
But how can I see, I see. How
That's
can I
yeah. That's a very good piece of intuition so far.
okay, that's good to hear. That's actually boost my morale a lot. Um so it's essentially two sets. Ah, so is it just like a set operation here? So we have two set of number
Mm-hmm.
and then we try to find the difference between not the difference. What's the other word? So we have difference
Intersection.
in the u or the intersection. The intersection between these two.
Mm-hmm.
And if the if the intersection is non-empty, then we have a valid, then all those numbers are traversable.
Mm-hmm. Yep.
Makes sense. Okay. Oh, okay. That's that. Ah, I see.
Yeah. Very good.
Ah, non-empty. Ah, I see. That's actually a really interesting way to think about it.
Yeah, it's like flipping the problem on
And
its head a bit. So instead of mapping numbers to
mhm,
so like
right.
right. So this is essentially we were previous doing is we're doing in square checks for every pair of numbers. When
Right.
instead you can identify core properties of every number and then
Hmm.
combine properties.
Right.
So there's a difference there. Okay,
I
great.
see.
Let's call the interview here. As
Hmm.
I always do, I want to ask you a little bit about any feedback that you might, or not feedback, any questions you might have, how you feel, and then I'll give you some feedback afterwards.
Yeah, definitely. I have a quick question about this problem.
Sure.
It's just that I cannot because like for a number there would be multiple primes to that number, right? So like
Yep.
let's say I have 18 for example. Well, not 18, but like some other numbers.
Sure. Yeah.
Uh, let's say I have like 10 yeah, let's say I have 10 for example, and that would
Mm-hmm.
be mapped to 5 and 2. So how can I choose? Do I combine like
Sorry.
find the
What's this
intersection
be?
of all? Oh, oh, sorry. Sorry, there should be 10. That's what I was supposed to. Yeah. So how can, because right now,
Uh huh.
like 10 can only be reached by if it's um I would only know that 10 can is traversable to 6 and then to 3. So this is still a valid array, right?
Yeah, that's still valid. Yeah.
But like but my only question is that how can I know to like combine this
Mm-hmm.
with this list? I
Yep.
mean, not combine, but like intersect the
I
two
know.
of
Yeah.
them.
Mm-hmm.
Yeah,
Yeah. So
instead
this
of
is
like these two.
yeah. So the optimal solution is not with set intersection either. That is just a stepping stone piece of intuition. The optimal
Hmm.
solution is with a data structure known as a disjoint set. Have you heard of those before?
Yeah,
So disjoint set
yeah.
lets you have use. So disjoint set lets you basically combine the five group into the two group because you know that they have tens. Now, how familiar with union find are you? The union find algorithm because this problem is basically there's two levels to the problem. There's the can
Hmm.
you just solve it with BFS, which is like okay great you can do it, and then
Hmm.
the optimal solution is recognizing that prime factorization with a fixed input size, so the fixed input being the number of bits,
Hmm.
lets you use union find in a disjoint set, and it gives
Hmm.
you a very interesting merge property because in this case, you know that the parent of 10 is
Hmm.
2, and you're currently
Right.
trying to check parent of 5, a parent of 10 with 5. So imagine you have some other numbers in here, like 25, which is not a parent of 2, right?
Hmm.
So what this lets you say is say, okay, I can set the parent of 25 to 10, and I can set the parent of
Hmm.
10 to 2. And
I
before you
see.
know
I
it, you've
see.
set the parent of everyone to 2 essentially, or or,
Ah, I
or the
see. I
or the
see.
smallest one. What no, 2 is in this example, other one, right? In this example, you would have set the
Hmm.
parent of 3 to 2 as well, right? Because you have these two,
Ah,
you
I
have
see.
shared. Because 6 would have been 2,
I see.
right?
Hmm.
So in this case, what you would have done is you would have union merge, right? Merge all of the items into the parent set, and you would check that the parent set has the same size as the input array, and therefore you
I
know
see. I
that
see.
it is traversable.
Ah, I see. I see.
So the set intersection is just a stepping stone. So that's not actually the optimal solution. It actually still would
Uh-huh.
be an improvement over what you originally wrote, because um, the size of each, the size of each, what are these are like the size of each set will still be strictly less than array, and therefore
Hmm.
intersection will still be an improvement of the algorithm. But the intersection was meant to be a stepping stone for you to realize that intersection doesn't mean that you actually intersect the numbers, you intersect the parent property, which is
Hmm.
the prime factorization.
I
So
see. I
so
see.
yeah, this is a difficult problem, right? It's not meant to be easy. You want a difficult problem, we can go there, right? So let's talk a bit about that before we call it here. Overall, I think this is still pretty well done, at least in terms of the base implementation, right? So you clarify things pretty quickly. I did give you an example just to help things along, but you understood that pretty quickly. That was good. You immediately identified that this could be framed as a graph problem, which is good. You clarify what GCD was. That was good. Now, generally speaking, a lot of these problems, the eco problems, if it's a math problem, you should start off by asking if you need to implement the math functions, because, I mean, if you C++, I just checked online. It is GCD is a built-in function in the STD, right? Um,
Mm-hmm.
if it's a if it's a LeetCode interview and the focus is not on math, then they probably won't want you to implement it. So you can always
I
just
see.
potentially save a bit of time by just asking them, hey, do we need to do that or not? Okay.
Mm-hmm. I see.
So just ask that. Uh, Initial explanation being top down was quite strong. Good to check on the input limits, right? The size of the integer. I didn't actually know the integers and C were so small, but that's not a big deal. It just depends on
Yeah.
language. The integer doesn't really care about that kind of stuff. A couple of things I
Mm-hmm.
saw were good about the graph generation as well was that you didn't generate all of the edges all at once. You only generated them under specific conditions, which was strong, and the implementation BFS was good. Now, one thing I do want to say was that I think you spent a bit too much time trying to do the graph generation, right?
I
Um,
see.
I don't know if you were just unsure how that part worked. If that's the case, then it should be pretty easy. Just go practice a bit more graph generation, right? I
Mm-hmm.
think in terms of the level of difficulty for this problem, um, there's no chance you can get to the follow ups in reality if you spent this much time on graph generation.
I
So
see. I
because
see.
this is a bit of a negative signal for interviewers, they'll think you're a bit weaker, and so
Mm-hmm.
they unlike me, they won't bother asking you some of the follow ups. Okay,
Right.
so that's something
I
which you need
see.
to brush up a bit because that part took a bit too long.
I see. I
Um,
see.
the recognition that the property we're looking for is graph connectedness, that is the key part. That was correct. Um, you had a you did not have the correct justification for using the visited set, right? You said you need a visited set to prevent infinite loop. That's not true for BFS. That BFS will never get into an infinite loop because it will always put it will all because it traverses at level order. And so if there's a
Mm-hmm.
loop, it would just keep adding the next element of the loop into the same level, and it won't get stuck on it, right? DFS can get stuck in an infinite loop. So for DFS, a visit set is mandatory. But for BFS, it's not mandatory. It's just for optimization. So that might be something you understood, but you just miss said a little bit.
Um, Sorry, Leo. I'm like for that. Wait, I'm a little bit confused because like if I go to B and then I add A back to the to-dos list, wouldn't I be going back to A
If you go, if sorry, if
or
you're
B?
B, where's B?
Sorry?
What are you talking about?
Sorry, if like let's say if I have an edge between A and B
Yeah,
and I go to from A I go to B
yeah,
and then in B since this is like
yeah.
unidirectional, I would know would I not go to back to A if I didn't check if B is uh
Yeah, so how this will work is your traversal looks like this. You go to A, go to B,
mhm,
you will add A back into your visitor list. So when you go, so A, okay, so put it this way. So at the start, you will contain A in your to do.
right,
Okay,
right,
you
right,
will
right,
pop A, your to do will be empty. So your curve will be A and your to do will be empty. Okay,
right.
A has two children, B and C. So you will
Hmm.
have B, C, correct?
I see.
You'll pop B, your two will have C. You'll pop B, your two will have C. Okay.
Hmm.
Okay, now with B, you will add A to the you will add A back into the visit to the to do, correct?
Right.
So now your visit like this. Now you pop C. Okay.
Hmm.
Now the C has the next one D, so you do like this. So now
Hmm.
you go to A, D, and then you'll have D, B. But guess what? At this point, you have finished your traversal. That's all the nodes. So
Oh
you would never
no,
get
but I
stuck.
mean like because like I pop A here, right? Wouldn't
Yeah.
I add B and C back in
You.
for
Yes, you
A?
would. Yeah, you would. Yeah. But that's okay because there's no there's no infinite loop here.
Oh, I see, I
Right,
see, I
you
see. Oh,
finish
I see.
traversal. BFS will never get
I
stuck.
see.
Yeah.
I
So
see.
you misspoke there. So that is something which you need to be careful of because in
Hmm.
DFS you actually will get in a loop. In BFS
Hmm.
it will just be optimization, but you will not get stuck in a loop.
I see, I see. Okay. I'll keep note of that. Sounds good.
Great. That should be it for this. And anything else that you want to mention last minute?
Uh, yeah, just like a really quick question
Okay.
because we're kind of running late. How do I know which part that it's like it's really simple and I should just gloss over it without sounding like I'm
Just
not
ask.
explaining it well enough.
Just ask. Can we assume that the
Oh,
graph can be generated like this? Can we do this? Can we do that? Ask those kind of things. Most of the time, interviewers say no, you have to implement it. Then just implement it. But you're not worse off, right? That's the same difference as before. But now you asked. For
I
example,
see.
this
Okay,
time you spent
sounds good.
about 3 minutes looking at GCD. You could have saved those 3
Uh,
minutes. For the
That's cool.
graph generation,
Okay.
this one you would have to implement, but that is on you. Like you just need to be faster on that one.
Oh, I see.
Yeah, if you
Okay.
want to do Leetcode hards at this level, for like the Leetcode hard for this level, the this would be like a borderline solution. Like if everything else was strong, if you had other strong attributes, this would be okay. If you
Mm-hmm.
come in here and the interviewer is told to check your technical ability, this will not count as a pass because this is not
I
efficient
see.
enough. So that is kind of the
Okay.
borderline we're talking about. Okay.
Sounds good. I'll keep that in mind. Thank you so much.
Great. Thank you.